Now starting. All attendees are in listen-only mode.
Okay. Good afternoon, everyone. My name is Nancy Holm. As most of you know, I'm Assistant Director here and also organize the seminar series. And welcome to today's seminar for those here and then also those listening online. This is one of the seminars in our semester-long series on multiple facets of sustainability. So I'd like to mention, as usual, that we'd like you to hold your questions to the end if possible. It's a little easier for those in the audience when we're not interrupting the speaker throughout. And then also for those listening online, you can type your questions in and we'll take those at the end also. So thank you very much. So today we're very pleased to welcome Dr. John Rogers to present a seminar for us. Professor Rogers obtained his BA and BS degrees in chemistry and in physics from the University of Texas in Austin. He also then received SM degrees in physics and in chemistry from MIT and a PhD degree in physical chemistry from MIT also. From 1995 to 1997, Dr. Rogers was a junior fellow in the Harvard University Society of Fellows. And during this time, he also served as founder and director of Active Impulse Systems, a company that commercialized technology developed during his PhD work. He joined Bell Laboratories as a member of the technical staff in the Condensed Matter Physics Research Department in 1997 and served as director of that department from the end of 2000 to 2002. He's currently the V.J. Flory Founder Chair in Engineering at the University of Illinois, with a primary appointment in the Department of Materials Science and Engineering, and he also holds joint appointments in a number of other departments on campus. He currently serves also as the Director of the Nanoscale Science and Engineering Center on Nano Manufacturing, which is funded by NSF. Dr. Rogers' research includes fundamental and applied aspects of nano and molecular scale fabrication, as well as materials and patterning techniques for unusual electronics and photonic devices, with an emphasis on bio-integrated and bio-inspired systems. He's published more than 350 papers and is an inventor with over 80 patents and patent applications. So we're very pleased to welcome Dr. Rogers.
Okay, thanks for that intro. It's a pleasure to be here and to talk to you about some of the work that we've been doing in my lab over the last 3 or 4 years or so. And it's an effort that's geared toward the development of electronics that can dissolve in water. And so I'll tell you about motivation, a little bit of perspective, a background, why we're interested in that type of technology. Step you through some materials options and some chemistry associated with the devices that we've built, and then provide you with some examples of different systems, give you a sense of what the level of technical sophistication is at this point in the development of this technology. So by way of perspective, I put up a slide that kind of describes something you probably already know, which is that electronics technology has been evolving at a very rapid pace, starting from decades ago when the kind of computer systems and electronic devices you would see are very large, integrated circuits and systems designed mainly for industrial or scientific computing. And then over time, the individual devices have gotten smaller and smaller, so you can pack more and more power into a device such that this kind of computing sophistication now exists, in this kind of format. And that's, Moore's Law. It's all about miniaturization and improving levels of functionality and the operating speeds. That's sort of the technology evolution. The societal implications are also profound because it's gone from kind of a niche technology to something that really permeates every aspect of our daily lives. And instead of just using computing devices to do computing, you're using them now to do communications, entertainment, productivity enhancement, and so on. So if you think about the future then, one future is already laid out by the semiconductor industry, and it's all about just continuing this trend out into the future. So smaller devices, faster integrated circuits, and cheaper devices as well. And what you're seeing is that there's an acceleration in that size miniaturization. It's not just happening at a constant rate, it's actually exponentially increasing in development time. And the consequence of that is that the lifetime, the useful lifetime of a device like that is no longer limited by the lifetime of electronics. It's limited by the lifetime of that particular generation of device. And so as a result, people get rid of their smartphones not because they stop working, but because they want to upgrade to the latest and greatest device. And that's a real testament not only to the speed with which innovation is happening, but also the extreme engineering sophistication that really allows these integrated circuits to have an infinite lifetime, in any practical sense. And that was one of the most compelling aspects of transistor technology, is it didn't involve vacuums or moving parts. And so in principle, you could engineer it to be everlasting. And in some practical sense, that goal has been accomplished. And so from the very earliest days, people thought about how to make devices last forever. And that's fine, but in the context of what I just told you, it may outstrip the useful lifetime for a device. You don't need them to last forever because people get rid of their consumer electronics more rapidly than that anyway. And so partly for that reason, and partly for a number of others that I'll describe to you, we got interested in building electronics that could operate at a very high level in a very stable fashion, but only for some well-defined period of time. Maybe programmed into the level of materials, or maybe triggered by some external event, after which they would simply degrade in, let's say, biologically or environmentally benign fashion. So imagine then integrated circuits built out of constituent materials that are water-soluble and biocompatible, for example. So that led us to think about bio-resorbable electronics, and thinking about engineering an integrated circuit with that characteristic is totally different than anything that's been attempted in the mainstream industry, but I think it's becoming something that's worth thinking about. And I know you guys, in terms of sustainability, it may help to address, an accumulation of electronic waste that's becoming more and more serious problem. So that's the perspective, what we hope to do. I think bio and eco-resorbable is one subset of a broader class of electronics technology that we're referring to as transient, in the sense that the devices physically disappear, like dissolution, resorption, sublimation. You can imagine a number of different mechanisms, but anyway, physically disappearing, but at engineering levels of control around the rates and the particular times when that dissolution or disappearance begins to happen. So that's a technology that we're interested in. There's a lot of interesting topics and materials surrounding realization of electronics like that. But if you go down a research path like that, it's useful to think about what would be a consequence of a successful scientific effort around that kind of technology. In other words, who would care about it if you could succeed? And I think there are kind of three broad use cases that we have in mind that would complement the kinds of devices you can build with integrated circuit technology that exists today. The first is a class of device that you could implant inside the body. So imagine a system that goes in at a wound site, does some kind of monitoring of that wound, or introduces a therapeutic process on that wound to accelerate wound healing. That would be a great kind of device to have, but you wouldn't need the device there once the wound healing process is completed. In that case, there's just a finite useful lifetime, after which you would ideally like the device to simply resorb into the body to eliminate unnecessary device load. So that would be one example in sort of a bio-resorbable type of mode of use, therapeutic or diagnostic. There are lots of things like that. Another broad area would be in environmental monitoring and sensing. So imagine if you have a chemical spill, or you want to do large area monitoring, you might want to distribute wireless sensors across that area in large numbers to provide useful information that would help you to remediate and clean up that spill, for example. But once the spill is contained or controlled, you might not need the monitors anymore, but at the same time, it might be daunting or wasteful to have to go back into the environment and pull them all out. So some kind of monitor of that sort, which would eco-resorb, would be interesting. And then this is really a problem that you guys think a lot about, is how to reduce electronic waste. And so this is a pretty aggressive goal in terms of where we are right now with the technology. But imagine a cell phone that you could wash away down your sink, you know, once you're done with it and you're ready to upgrade to the next generation. That would be pretty interesting if you could do that. A lot of daunting technical challenges, but that would be a vision, or at least some fraction of the component parts of something like a cell phone, water soluble in that sense. So, like I said, we've been thinking about this for a while. I think this was the first paper that we published. It was basically an example of a silicon electronics technology where we were using a substrate and encapsulation layer made out of purified silk derived from silkworm cocoons. And silk is interesting because it's bio-resorbable, it's FDA approved, it's already used in resorbable sutures, and we figured if you could combine that with electronics, then maybe you could make something that's partially bio-resorbable. And we did some basic evaluations. We take this kind of platform, the transistors and integrated circuits are there, the silk is there, implant them, you know, under the skin of in an animal model, and then come back a couple weeks later and see the silk's completely gone. There's no inflammation. Now the transistors remain. So this was not a fully resorbable but device technology, but at least something that we could do and start to think about. So you know, you'd have to engineer this system such that the transistors are not causing a problem with the biology, but you know, a large fraction of the overall device is disappearing because it's made out of silk. So that's one baby step in this direction. The other way that you could think about using a bio-resorbable system is a way to you know, combine it with something that's non-resorbable, like I showed you before, but for a specific purpose. So, for example, here's a thin open mesh array of electrodes. You'd like to integrate that with the brain. The brain is highly curved and textured, so you want that array of electrodes to be as conformal and floppy as possible. But when it's floppy enough to conform to the brain, it's no longer rigid enough to handle. So you can imagine using a temporary sheet of silk just to provide a way to mechanically manipulate this electrode array and mount it on the brain, where you would then dissolve the silk away, leaving just the mesh electrodes that could drop down into contact with that textured surface of the brain. So this would be an example of utility in something that's partially resorbable, but again, not quite the grander vision that we had in mind that I outlined previously. So the question is, how do you get to something that's fully resorbable? We've been thinking about that problem. A number of other groups as well started in this area, one at Stanford and one at Johannes Kepler in Germany. In Stanford, they're attempting to use organic polymer-based materials for the active components of the devices. So they have a polymer-based semiconductor, a dielectric, they have a plastic substrate. They're still using regular metals as the gate electrode and the source and drain electrode of the transistor. So this device is also just partially resorbable, but it's a different sort of complementary approach to what the kinds of things that we were pursuing. In Germany, they're trying to use natural materials or materials inspired by nature to do the same thing. So again, it's organic-based, but really sort of biomaterials or naturally occurring materials. So as an example, they were using caramelized glucose as a substrate. So it's kind of interesting, different way to think about it. If you build devices with synthetic polymers or ones that are found naturally, you can make transistors that switch back and forth. So in principle, you could conceive of an integrated circuit technology, but the performance is modest, you know, bordering on lousy compared to silicon. So the range of applications you could address are very limited as a result. You could never do a computer, for example, a microprocessor would be sort of out of the question. So some limitations, but anyway, just some evidence that other people are thinking about this as well. I think if you could do it with silicon, then that's the way you would go, because you would be building on a really well-established basic scientific knowledge and manufacturing capability derived from conventional silicon integrated circuits, and then you know, possibly being able to use that in a resorbable format. And what we found is that silicon itself will undergo hydrolysis. It will dissolve at physiological pH in aqueous solution and physiological temperature. The rate is very, very, very slow. So just a few nanometers of silicon will dissolve per day. But if you think about using silicon in very, very thin formats, that might be fast enough for the kind of applications I outlined previously. So this is an atomic force image, a microscope image of a little platelet of silicon. It's about 50 nanometers in thickness in this case. Now, as a function of time after immersion in aqueous solution with these conditions. And so you can begin to see it disappear. If you plot the height or the thickness of that silicon as a function of time, it just has a very linear decrease in thickness with time. And for something that starts out about 90 nanometers thick at physiological pH, it's slightly basic. And these kind of temperatures, it's almost completely gone in 3 weeks. And the product of that dissolution is silicic acid, so SiOH4. This is naturally occurring in your body. It's found in reasonably high concentrations in seawater, for example. So conceivably, at least at the dosages that we're talking about here, both bio and environmentally benign. And so that is sort of an interesting observation, because if silicon can dissolve like that, provided you're using it in sufficiently thin film forms, then you can go off and build high-quality devices. Now, the detailed materials chemistry of how that's dissolving and the kinetics of the hydrolysis are extremely important, and they depend on all sorts of things. They depend on temperature, room temperature. Things are much slower than at body temperature, which might be expected. There's also a strong dependence on pH. So as you go more and more basic, the rates for dissolution go up. So you're a little bit acidic here, mildly basic, a little bit stronger basic conditions, and you can see what happens to the rate. 1 nanometer per day, 15 nanometers per day roughly, to 25 nanometers per hour at a pH of 10. So very sensitive to that. And so the dissolution, you have to think about where it's being placed in the body, whether it's going to dissolve given the pH conditions, and likewise in the environment. But at least, you know, in a range that's sort of reasonable here, it will dissolve, although very slowly it goes away. It depends, though, on doping level. So you add phosphorus or boron, then the rates decrease substantially, but they're still non-zero. So given a long enough time, they begin to disappear. You can see what happens. You put it in bovine serum, room temperature, and at body temperature. You can see the different rates there. Serum has a pH of about 8.7. There's buffer saline. This is seawater, pH about 7.8. You can see the silicon go away there. And so again, it's tied most closely to pH, but other ion content in the solutions could conceivably have an effect as well. But that's where the material science comes in, and we're studying a lot of those issues. It's ongoing. Well, what's the significance? So I mentioned this several times. So if you think about transient electronics, you can use silicon provided it's very, very thin. So it turns out you can make good devices with silicon only 30, 20 nanometers in thickness. If it's that thin, then the dissolution time is only 10 days, a couple weeks. And for a representative chip size, the amount of water required to dissolve the silicon is small, maybe half a milliliter before you hit solubility limits in the silicic acid. Now, if you compare that to the kind of silicon electronics you find in your laptop or your cell phone, you see some notable differences. So the silicon thickness in that case may be 700 microns, not millimeters, microns. And if you extrapolate these rates to that thickness, then the dissolution time, 600 years, and you need a lot of water to do that. So a conventional silicon wafer platform is not transient in any way that we would consider it to be. And so thin silicon is critically important then. But not just silicon, you need other component materials to make an integrated circuit. So you can start looking around and thinking about what kind of metals are available, dielectrics, substrates, encapsulating layers that would allow you to build a full circuit that's water soluble and also biocompatible. And there are a number of options. Here's one example. We like to use magnesium as interconnect wires and electrodes, magnesium oxide as a dielectric. If you put all those things together, silicon, magnesium, magnesium oxide, you can make integrated circuits. You put them on silk. I already talked to you about that. You can make circuits that are water soluble in their entirety, and that's kind of what we had in mind when we started in this field. So, as I mentioned, silicon, is a well-known material. There are well-known device architectures. So, almost immediately, you can go off and build all of the component building blocks that you might be interested in for an integrated circuit. So, here's a transistor, very good switching characteristics, factor of 1,000 or 10,000 times better than what you can obtain with organic alternatives. You can make simple logic gates that behave in an expected way. You can also make photodetectors and diodes, and this is just an imaging array. It's an array of ultra-thin silicon photodetectors, and you can take pictures with that kind of image sensor, but at the same time it's made out of completely water-soluble materials. A lot of times you need to worry about powering these devices. Turns out you can do primary batteries that are water soluble. You can also do silicon solar cells. So you need a little bit more silicon, thicker, but if you're paying attention to light trapping and so on, then you can do silicon solar cells with reasonable efficiencies as a potential power supply for these devices. So this is what it looks like then if you put them in water. This is a simple test platform, very simple circuit, like the one I showed you before. Silk is the substrate. This is just a beaker of water, a petri dish of water. And what you see here is as the circuit begins to dissolve, what disappears first is the silk. It's treated so that it's essentially in an amorphous state, so its rate of dissolution is very fast. Once it's gone, the circuit components themselves are not mechanically strong enough to hold together, so it kind of disintegrates at that point. After disintegration, then you begin to see the magnesium traces themselves undergo hydrolysis to magnesium hydroxide. So over the course of a few hours, the magnesium will completely disappear. The silicon takes a lot longer, but the silicon is so thin, so small, you don't really see it here. But it, as well, given enough time, will disappear. So that's what it looks like. So you can imagine what it would look like in the field. This is just an example. So you can take these devices, let's say, drop them into the grass or something, and then simulated rain coming down. See how it kind of washes away, essentially. So it's silk, magnesium, and silicon. That's pretty much it. And very tiny amounts of material. You think about these are very, very thin sheets, and so minimal amounts of material coming as a result of the dissolution. So you might wonder, that's awfully quick for a device to disappear. What if you want, in a lot of cases you want it to last a lot longer than that. And so ways to control the transience time then involve strategic selection of the substrate and the encapsulating layers. So you build in water barriers so that the circuit components themselves are not dissolving away. But those water barriers themselves are slightly soluble, but soluble at a controlled rate. And so once they're dissolved away, then the circuit will start to disappear. So here's an example. We've used silk, in this case treated so it's very crystalline, so its rate of dissolution in water is very slow, and it's sealing the circuit away from the water, so the circuit doesn't dissolve either. It's a little bit hard to see with this light. You see a little bit of wrinkles here. That's because the silk is swelling a little bit, but it's not dissolving away, and the circuit is still functional, and it still remains. So that's the strategy for building in well-defined lifetime in an overall system that will nevertheless eventually disappear. So and from an engineering standpoint, you need to know exactly the kinetics of how things are dissolving so that you can design the system to behave in the way that you want it to behave. So a lot of what we do is look at how quickly different materials are dissolving, modeling that rate of dissolution with analytical models so that we can use those as engineering tools to do the system design. Here's an example of a time sequence of images for a serpentine trace of magnesium. And as you can see, just in a few hours, magnesium will completely disappear. You can measure the resistance, and you can see that disappearance. So here it is, just in a couple of hours, the resistance will go from a very small value to a very high one. Now, if you encapsulate the thing, you add magnesium oxide on top, it dissolves at a slower rate, so you have very little change in resistance, and then magnesium oxide is gone, then the resistance starts to increase rapidly as the magnesium is dissolved. And then likewise, you use different thicknesses of magnesium oxide. You add a layer of silk. This is magnesium oxide plus silk, and you can get it into the range of a few hundred hours without too much trouble. So the point is you have a period of stable operation followed by a relatively quick period of dissolution. And you can see that even more explicitly in this transistor array. So there's an array of transistors down here encapsulated. And what you see is these are various performance metrics, mobility, on-off current, and threshold voltage. You monitor those over time. And what you see is very stable, rock-solid operation up until the time when the encapsulating layers are now dissolved away. At that point, the silicon and the magnesium starts to dissolve because they're exposed directly to the water, and then you have a rapid, catastrophic degradation in the electrical properties. So this is the way that you would think about making something that has stable operation followed by rapid disappearance, and that's one way to do it. So you do individual devices. This is an example of a slightly more integrated system, just to give you a sense of where we are in trying to mature the technology. This is a full-wave rectifier. So I mentioned power before. One way to deliver power is to use radio frequency signals like coming out of your cell phone. You need something to rectify that RF energy and then supply the DC power to the circuit or the other device components that you might be driving. This is a circuit that does that. This is all out of magnesium, silicon rectifiers, p-n junction diodes here, capacitors, and an inductor over here, resistor. And then we have a mounting place for an LED, and you can glue an antenna over here just to show that the device is working. So this is what it looks like. It's not the most beautiful thing, but you see the circuit there. This is a magnesium antenna, and then we're shining RF radiation on this thing at about a power level comparable to what you get out of a cell phone at 900 megahertz. And this circuit is operating, and then it's supplying power to that LED. So this is one way to do things, and this is particularly valuable for devices that would implant into the body, for example. You can deliver power from the outside through the skin into a rectifier like that to operate an implant. So silicon looks promising. It's not the only material that you can think about as a semiconductor for these kind of water-soluble circuits. There are a variety of metal oxides that are attractive for various purposes. Zinc oxide is one of them. You can just deposit that by sputter deposition. It will undergo hydrolysis to zinc hydroxide. So if you combine that with magnesium oxide, you can make transistors based on zinc oxide. That's what one of the devices looks like right after fabrication. Now it's immersed in water, and you can see everything gradually dissolves after half a day or so. So that's another option in terms of materials. Zinc oxide is nice because you can do transistors, but you can also do mechanical energy harvesters instead of RF, in which case bending the substrate can generate some amount of power. So this is a test platform array of those zinc oxide transistors, and then these are energy harvesters over here, mechanical energy harvesters on silk. So the whole thing is completely water soluble, as illustrated there, but at the same time you have decent electrical properties in terms of switching parameters of the transistors, and then these are the energy harvesters. So what's being shown here is the voltage output as a function of time as we're cyclically bending these things back and forth. So if you get about a volt and some small modest amount of current, you can see the spikes going up and down, and we've shown that you can get enough power to operate a pacemaker, for example. So mounting one of these things on the heart would be a way to internally supply power to an implant. So I think the environmental aspects are intriguing to us. A lot of our focus, though, is on these medical devices that can be used for advanced applications in human health care. And so we're interested in biocompatibility. I showed you the silicon-on-silk transistors where the transistors weren't resorbable before. These are some additional experiments now with fully resorbable circuit technology. You can implant it under the skin, you come back, and you can examine the animal to look for inflammation or adverse reaction. You have to do a lot of histology studies. So we've done about half a dozen animal evaluations in this way, and we haven't seen any adverse consequences of this type of device. So that's not, anything close to FDA approval, but at least it's indicating that it's a reasonable thing. I should mention that the silicon itself gets converted to silicic acid. That's naturally occurring in biofluids anyway. Magnesium has been used as a resorbable intravascular stent in the past, so there's some basic knowledge on biocompatibility of magnesium, and silk is already FDA approved. So it's a reasonable collection of materials to think about implanting into the body. So what would you do with that? In particular, I mentioned a couple of things. Let me give you a specific example. So if you go into the hospital and you have an operation, it turns out that the leading cause for readmission back into the hospital is infection at the surgical site. And that's typically treated with drugs, but more and more folks are seeing antibiotic-resistant strains of bacteria. And so we thought about maybe like an electroceutical approach instead of a pharmaceutical one, in which you build a thin film piece of electronics as an applique that would go into the body at the very tail end of the surgical operation and then remain there when the skin is sewed up. And the device would be configured such that you could wirelessly deliver power to this device, and the device would create well-defined amounts and spatial distributions of heating local to the site of surgery to do in situ sterilization, to kill bacteria as they might be forming. But in this case, you really only need the device for a period of 2 weeks or so, because once a patient moves beyond that period, the incidence for infection are very, very small. So you'd like the device then to naturally go away after 2 weeks to eliminate that unnecessary device load, and that's what this component is designed to do. You can see its IR camera. You can heat up well-defined locations under the skin, and then this thing dissolves over time. About three weeks, it's gone essentially. So that would be one. And so that's kind of where we are. Let me try to give you a sense of what is possible. We've demonstrated, and I just showed you a fraction of these kind of components: sensors, devices, and then integrated systems. We do a lot of different kinds of measurement: temperature, thermal conduction, impedance for skin hydration, for example. We measure electrical potential, strain, stress, light. I showed you the camera, mechanical vibrations of that zinc oxide harvester. We measure flow and pressure. We've done transistors, diodes, rectifiers, photodetectors, resistors, capacitors, inductors, antenna, wireless coils, solar cells, and then in some cases we've taken these kind of components of these and then put them into very simple systems, but at least things that have overall function. So I think it's still very much early days in the development of this technology, but we can already do a fair number of things and hope to expand on that over time. So one additional point I'll just make is that the materials appear to be biocompatible and implanted. They're also safe to eat, and in fact they're good for you, because if you look, it has magnesium, it's got silk, it's got silicon. If you look at a daily vitamin, one single vitamin tablet has about 300 milligrams of magnesium and 10 milligrams of silicon. That's 3,000 times more of those elements than are found in that circuit. So it's because these films are so thin that the total mass content is minimal. And by the way, it's the same elements are found in daily vitamin anyway. So it turns out you can actually eat these things. They're edible as well. And I actually have eaten one of these things myself one time, just one time only. And it was really a response to a bet by a DARPA program manager who was funding the work. So I ate one of these things as part of a keynote talk that I gave in December, just to show that you could, in fact, do that. So that's kind of a summary of where we are. It's still early days. Our very first paper on this technology was just in September, so we're learning as we go along. But it seems like we have a lot of basic components, the building blocks to do some useful things. I should acknowledge our senior collaborators. This is highly collaborative efforts. The silk experts are at Tufts. Young Ong at Northwestern does all the modeling, that dissolution modeling. Placid Ferreira on manufacturing. You have to come up with some unusual approaches to make these circuits, because the materials themselves wash away in water, so that eliminates some processing options. And then we've been working with Lincoln Laboratory to try to bring this kind of technology in alignment with the kind of foundry fabs that are used to make conventional integrated circuits. Because I think if you could do that, then you could reduce the cost and increase the sophistication beyond what we're doing right now, which is basically by hand fabrication by graduate students. So with that, let me go ahead and conclude. I have another little movie here that sort of run in the background, but yeah, that's where we are. I'd be happy to answer questions if you have any. Thank you.
Yeah, I know a lot of biologists are always trying to track organisms and unique transmitters. I just was wondering whether these could be used to transmit locations for organisms moving about the environment.
Yeah, potentially. I mean, I think the key is achieving radio frequency transmission and providing some kind of source of power. So we have an RF way to deliver power. In separate programs, we have operating radios. We have not built a fully functional radio that's completely transient, but where a lot of the component parts are. So I think it's within the realm of possibilities. It requires a little bit more engineering capability than we have at this moment. But I see it as an option and something that we'll demonstrate before the end of the year, that type of thing. Yeah.
Any questions?
Have you used any reason like graphics or like muscle stimulation?
Yeah, we have a proposal that was funded recently on nerve stimulation. So we have a plan that we put together. I don't have devices that we've built and tested, but I think that's a great idea. Muscle stimulation, you can also stimulate nerves and mitigate pain in that way, for example. And it would be a great type of application because the pain might go away. You don't need the device anymore, for example. So yeah, those are great ideas. Bone stimulators as well to drive bone growth. I think there are a number of things you can do. So I think in terms of technical challenge, that's a lot more feasible than, say, a long-range radio, just in terms of where we are right now, because we know how to do inductive delivery of power down into the body. The stimulator just requires a rectifier and some electrodes. So I think it's well within the realm of things we can do even today.
Say a little more about the electrical power necessary for one of these implantable devices. Do you need a device close by? Or
Yeah.
do you envision doing it from all the radio waves that are out there already?
Yeah, so a couple things. So you can either do far field radio frequency transmission, at frequencies comparable to your cell phone. That'd be one way to do it. So your cell phone's putting out about a watt or two when it's looking for a cell phone tower. So there's a fair amount of power coming out of this thing. For the amount of power you need to do the heating to kill bacteria, it only requires a few degrees temperature increase. So this is milliwatts. This is watts. So you can do that. I mean, you can't be infinitely far away, but if you're close enough, that's a reasonable thing. This is not far field. This is near field coupling. So at much lower frequencies, more of an inductive power transfer. And there, you really have to be pretty close to the skin, more than a centimeter away, and the coupling efficiencies are very low. So it depends on what you're doing. But yeah, you can deliver a lot of power with light LEDs, run heaters. You can operate radios, in this realm without exceeding thresholds that would be dangerous, right? So.
Any other questions here?
Yeah, I was wondering if there's other applications that you're looking at for the dissolution of some of these materials, other than what you have.
Yeah, a lot. I mean, in terms of the materials choices, there are a range of bio-resorbable materials that are already used and are FDA approved for implants. So PLA, PGLA, PCL. They're not used in electronics context, but they already have a vast database of information on biocompatibility. And we're looking at sort of repurposing those materials for electronics. So I think for the substrate and encapsulating layers, there's probably 10 materials that you could look at. without requiring, the whole FDA approval process of the material itself. The metals, magnesium is great. It's an option. We've looked at others, molybdenum, tungsten, zinc, and iron. And all of those materials can be processed into the form of wires and electrodes. You can make integrated circuits out of them. Some of them are great. All of those materials have some information indicating biocompatibility, again, at the loading levels that would correspond to an integrated circuit. Some of them dissolve in a nice and controlled fashion. Molybdenum and magnesium are in that realm. If you look at iron or tungsten, to some extent zinc, it's much messier because they form oxides that then dissolve at completely different rates than the native metal. And so you get flakes, you get porosity that develops as it's dissolving. And for an implantable system, you don't want the thing to be fragmenting apart as it's dissolving, because then you get suspended chunks of stuff that could get into the bloodstream, for example, and cause big problems. So it goes beyond just the biocompatibility of the materials themselves and their capacity for dissolving in biofluids, but it's really the nature of that dissolution and how it's disappearing that becomes a really important consideration as well. So I think if you use all of those filters, right now molybdenum and magnesium look like they're the most attractive candidates.